illusion of a calm ocean. From a distance, the ocean appears settled. Its surface rises and falls in slow, repeating motions, reflecting light in a way that feels familiar and predictable. Waves approach the shore, break and retreat over and over again, as if the sea itself is breathing. For most people, this is the ocean they know. A wide horizon, gentle movement, a sense of space. It feels stable. It feels understood. It feels like something that has already been mapped, measured, and explained. But this impression is shaped almost entirely by what we can see. And what we see is only the thinnest layer of a system that behaves very differently beneath the surface. The calmness of the ocean is convincing because it hides complexity so well. Unlike mountains, which display their structure openly, or deserts, which reveal their harshness immediately, the ocean conceals its most active processes below a moving surface that rarely hints at what is happening underneath. The water does not ripple differently to signal instability. It does not darken to warn of shifting ground or hidden motion. Most of the time, it looks the same whether it is shallow or deep, stable or unpredictable. This visual simplicity is one of the reasons people often assume the ocean is fully known. It feels like something humans have already figured out. After all, ships cross it every day. Satellites observe it constantly. Maps show it neatly divided into basins and regions. But scientific familiarity does not come from crossing a place or observing it from above. It comes from sustained measurement, repeated observation, and reliable access. And in many parts of the ocean, those conditions are not easily met. Scientists do not avoid the ocean as a whole. In fact, marine science is one of the most active and ambitious fields of research on the planet. What scientists avoid are specific parts of the ocean where the environment does not allow consistency. Places where conditions shift too often, where the ground does not remain stable, where pressure overwhelms instruments, where currents refuse to behave predictably, and where small failures can grow into irreversible losses. Avoidance, in this context, does not mean fear or mystery. It means restraint. It means recognizing that some regions of the sea demand more than current tools, budgets, and safety margins can reasonably provide. One of the quiet truths about ocean research is that the sea does not become more predictable as you move away from shore. In many cases, it becomes less so. Near coastlines, there is at least a framework of reference. Depth changes are gradual. Communication with land is possible. Rescue routes exist, even if they are delayed. But farther out, the ocean transitions into a different kind of space. A space where depth increases rapidly, where weather systems have more influence, where currents strengthen and interact, and where the seafloor may lie kilometers below the surface. In these regions, the calm appearance of the water above has very little relationship to the conditions below. A ship can float over water that is nearly motionless at the surface, while powerful currents move steadily beneath it. Instruments can be lowered into darkness, where pressure increases silently and relentlessly. And once equipment passes a certain depth, recovery becomes uncertain, even if everything appears to be going according to plan. This disconnect between appearance and reality is central to understanding why certain ocean regions remain lightly studied. The sea does not resist observation in obvious ways. It does not block entry with visible barriers. Instead, it challenges research subtly. Pressure increases without sound. Temperature gradients shift slowly. Currents alter position gradually. These changes often go unnoticed until instruments begin to fail or data begins to behave unpredictably. Unlike environments where danger announces itself clearly, the ocean's challenges are cumulative. They build quietly over time and often revealing themselves only after a mission has already committed resources and effort. There is also the matter of scale. The ocean is vast in a way that is difficult to fully appreciate. Even areas that appear small on a global map can contain enormous variations in depth, chemistry, and movement. A single research vessel, no matter how advanced, can only observe a narrow slice of this system at any given moment. Measurements taken at one location may not represent conditions even a short distance away. This variability means that to truly understand a region, scientists must return again and again, deploying instruments repeatedly, maintaining long-term observation stations, and collecting data across seasons and years. In some parts of the ocean, this is possible. In others, the environment disrupts these efforts so consistently that long-term records remain incomplete. What makes this particularly challenging is that the most scientifically interesting regions are often the least cooperative. Areas where ocean currents interact strongly, where the seafloor is geologically active, where chemical gradients shift rapidly, or where unique ecosystems exist tend to be areas where stability is rare. Instruments deployed there may drift away, become buried, or fail prematurely. Ships may be unable to return to the same position due to weather or current changes. Timing windows may close unexpectedly. Over time, these disruptions accumulate, making certain locations unreliable for sustained study, even if they hold valuable information. It is important to understand that avoidance does not imply neglect. Scientists continue to study these regions using indirect methods whenever possible. Satellites measure surface properties. Autonomous vehicles collect short-term data. Drifting instruments sample water masses as they move. But these approaches cannot fully replace continuous, fixed observation. They provide fragments rather than complete records. And for many scientific questions, fragments are not enough. To understand long-term change, researchers need stability. They need locations where instruments can remain in place, where measurements can be repeated under comparable conditions, and where data gaps are minimal. When the ocean refuses to offer that stability, scientists must choose whether the risk of failure outweighs the potential reward. The illusion of calm plays a role here as well. Because the ocean appears steady, it is easy to underestimate how often conditions change beneath the surface. Currents shift slowly but persistently. Water masses with different temperatures and salinity slide past one another without visible boundaries. The seafloor may consist of soft sediments that respond to pressure and movement over time. These changes do not create dramatic events on the surface, but they alter the environment enough to interfere with measurement. Instruments calibrated for one set of conditions may drift out of range as the surrounding water changes. Anchors may lose their hold as sediments shift. Cables may experience unexpected strain as currents pull in different directions. None of these failures happen suddenly or violently. They happen quietly, and often going unnoticed until data quality degrades or communication with an instrument is lost entirely. There is also the reality that the ocean does not operate on human schedules. Research expeditions are planned months or years in advance, with carefully allocated ship time, equipment budgets, and personnel. But the sea does not adjust itself to those plans. Weather systems delay departures. Currents shift deployment sites. Seasonal changes alter water structure. Even when conditions appear favorable, small deviations can compound into significant obstacles. A delay of a few days can shorten an already limited observation window. A change in current direction can move an instrument out of the intended study area. A minor mechanical issue can become a mission-ending problem if recovery is not possible within the available time frame. This mismatch between human planning and ocean behavior is one of the most fundamental reasons some regions remain avoided. Not because they are impossible to reach, but because reaching them reliably, repeatedly, and safely is difficult. Science depends not only on access, but on consistency. Without consistency, data becomes fragmented. Without fragmentation, patterns remain hidden. And without patterns, understanding remains incomplete. Scientists are aware of this limitation, and they plan accordingly, choosing locations where the ocean allows a degree of cooperation, even if that cooperation is imperfect. The idea that the ocean is a single, uniform space also contributes to misunderstanding. In reality, the sea is divided into layers, zones, and systems that behave independently. Surface waters interact with the atmosphere. Mid-depth waters move according to global circulation patterns. Deep waters respond to temperature and density gradients established over centuries. Each layer has its own dynamics, and interactions between them are complex. When scientists avoid certain regions, they are often avoiding places where these layers interact in especially unpredictable ways. Areas where surface storms influence deep currents, where seafloor features redirect water movement, or where chemical exchanges occur rapidly across depths. These interactions are fascinating, but they are also difficult to measure consistently. Another factor that reinforces avoidance is the quiet cost of failure. When an experiment fails on land, recovery is often possible. Equipment can be repaired, sites can be revisited, adjustments can be made. At sea, especially far from shore, then failure can mean permanent loss. Instruments may sink beyond recovery. Data may be irretrievable. Ship time may be exhausted. Funding may not allow a second attempt. This reality shapes decision-making in subtle ways. Researchers must consider not only what they want to study, but what they can afford to lose. In regions where failure rates are high, even well-designed projects may be postponed or redirected. All of this leads to a pattern that can be mistaken for avoidance driven by fear or uncertainty. In reality, it is avoidance driven by experience. Scientists learn over time which parts of the ocean allow productive work and which consistently disrupt it. They share this knowledge quietly, through reports, planning documents, and informal conversations. Certain regions develop reputations not as forbidden places, but as difficult ones. Places where the ocean sets the terms, where data collection must adapt constantly, and where long-term observation remains elusive. The ocean is not one environment. One of the biggest misunderstandings about the ocean begins with language itself. People often speak about the sea as if it were a single place, a continuous body of water stretching from shore to shore, behaving more or less the same wherever you go. This idea is reinforced by maps that color the ocean in uniform shades of blue, by satellite images that show vast, uninterrupted surfaces, and by everyday experiences that rarely go deeper than the coastline or the surface layer. But for scientists, the ocean is not one environment. It is a layered system made up of many distinct regions, each governed by different rules, pressures, movements, and risks. And it is this internal diversity that explains why some parts of the ocean are studied regularly, while others are approached cautiously or avoided altogether. At the most basic level, the ocean is divided vertically. The surface layer interacts directly with the atmosphere. It absorbs sunlight, exchanges heat with the air, and responds quickly to weather. Beneath that lies a transition zone where light fades, temperatures shift, and water properties begin to change. Deeper still are layers that remain dark, cold, and relatively isolated from surface conditions. These deeper layers move slowly, shaped by density differences rather than wind, and they can remain stable for long periods before changing. Each of these layers behaves like a separate environment stacked on top of the others. And instruments designed for one layer may not function properly in another. Methods that work at the surface may fail entirely at depth. This vertical separation alone is enough to complicate research, but it is only part of the picture. Horizontally, the ocean is just as divided. Coastal waters behave differently from the open ocean. Near land, the seafloor rises gradually, sunlight reaches deeper, and nutrients are more abundant. These areas support rich ecosystems and are relatively accessible. Ships can return to port. Communication with land is possible. Equipment can often be recovered or replaced. As a result, coastal regions are among the most heavily studied parts of the ocean. But as you move farther from shore, conditions change. Depth increases rapidly. The seafloor drops away. Sunlight disappears. The influence of land weakens. The open ocean becomes a different kind of environment, one that is harder to access, harder to predict, and harder to monitor over time. The open ocean is often described as empty, but this is misleading. It is not empty in a biological sense, nor is it inactive. What it lacks is stability from a research perspective. Currents in the open ocean are stronger and more persistent. Weather systems have more room to develop. Waves grow larger. The distance from support increases. A research vessel operating far from land must carry everything it needs, from fuel to spare parts, and once a mission begins, there are fewer opportunities to adjust plans. In these conditions, even small problems can escalate. This is one reason why scientists are selective about where they work in the open ocean. Not every region offers the same balance of risk and reward. Another important distinction lies in the shape and composition of the seafloor. Some areas of the ocean floor are relatively flat and stable. Others are steep, fractured, or covered in soft sediment that shifts over time. These differences matter enormously for research. A flat, stable seafloor can support long-term instruments anchored in place. A steep slope or unstable sediment layer may cause those same instruments to tilt, sink, or be buried. In regions where the ground itself cannot be trusted to remain unchanged, maintaining consistent measurements becomes difficult. Over time, scientists learn which seafloor environments are cooperative and which ones tend to disrupt equipment. This knowledge quietly influences decisions about where to deploy resources. The ocean is also divided by movement. Some regions are dominated by steady currents that flow in predictable patterns. Others are shaped by turbulence, eddies, and shifting boundaries where different water masses collide. These dynamic zones are scientifically valuable because they play a major role in heat transport, nutrient distribution, and climate regulation. But they are also operationally challenging. Instruments placed in these regions may drift far from their intended locations. Water samples collected at one moment may not represent conditions even a short time later. The faster and more chaotic the movement, the harder it becomes to build a coherent picture of how the system behaves over time. This is another reason why certain ocean regions remain lightly studied despite their importance. Temperature adds another layer of separation. Some parts of the ocean maintain relatively stable temperatures year-round. Others experience sharp gradients where warm and cold water meet. These boundaries are not fixed. They shift with seasons, currents, and weather patterns. For scientists, this creates uncertainty. Instruments calibrated for one temperature range may behave differently as conditions change. Biological communities may move in response to these shifts, altering the very processes researchers are trying to observe. In regions where temperature boundaries move frequently, maintaining consistent measurements requires constant adjustment. In some cases, the effort required outweighs what current research programs can reasonably support. Salinity, The amount of dissolved salt in seawater also divides the ocean into distinct environments. Differences in salinity affect water density, which in turn influences how water moves vertically and horizontally. Regions where freshwater input from rivers or melting ice mixes with salt water can behave unpredictably. Layers of water with different salinity may slide past one another, creating hidden boundaries that affect current flow and chemical exchange. These invisible divisions complicate sampling and measurement. Instruments lowered through the water column may pass through multiple environments in a short distance, each with its own characteristics. Understanding these transitions requires dense, repeated measurements, something that is difficult to achieve in remote or unstable regions. Light is another factor that fragments the ocean into separate worlds. Sunlight penetrates only the upper portion of the sea, and even there its reach varies depending on water clarity and angle. Below a certain depth, natural light disappears entirely. This absence of light shapes ecosystems, chemical processes, and physical behavior. It also limits observation. Cameras require artificial illumination, which can disturb sensitive organisms and alter behavior. Some species avoid light altogether, retreating deeper when illuminated. In these environments, observing without interference becomes a challenge. Scientists must decide whether the data they collect truly represents natural conditions or reflects the presence of their instruments. In some areas, this uncertainty leads to cautious approaches or limited study. The ocean is further divided by time. Conditions that appear stable during one season may change dramatically in another. Storm patterns shift. Currents strengthen or weaken. Biological activity rises and falls. Some regions are accessible only during narrow windows when weather and sea state allow safe operation. Outside those windows, conditions may be too rough, too unpredictable, or too dangerous for sustained work. This seasonal variability means that some parts of the ocean are studied intensely for short periods and then left alone for the rest of the year. Over time, this creates gaps in data that are difficult to fill. All of these divisions, vertical layers, horizontal regions, seafloor types, movement patterns, temperature zones, salinity gradients, light levels, and seasonal cycles combine to create a mosaic rather than a single environment. When scientists talk about avoiding certain parts of the ocean, they are responding to this mosaic. They are not making broad judgments about the sea as a whole. They are identifying specific combinations of conditions that resist reliable observation. A region might be accessible but unstable. It might be scientifically interesting but operationally hostile. It might offer valuable short-term data, but make long-term monitoring nearly impossible. There is also a cumulative effect to consider. A single challenging factor can often be managed. Pressure alone can be addressed with stronger housings. Darkness can be addressed with artificial light. Distance can be addressed with better ships. But when multiple challenges overlap, strong currents combined with unstable seafloor, or deep water combined with limited communication and narrow time windows, the difficulty multiplies. These overlapping challenges define the parts of the ocean that scientists tend to approach with caution. They are not impossible to study, but they demand a level of effort and risk that must be carefully justified. This selective approach is not static. As technology improves, some regions become more accessible. New instruments, autonomous vehicles, and improved modeling allow scientists to gather data from places that were once unreachable. But even with these advances, the fundamental structure of the ocean remains the same. It is still divided into environments that behave differently and resist uniform treatment. Technology may shift the boundaries slightly, but it does not erase them. Understanding that the ocean is not one environment helps explain why gaps in knowledge persist. It explains why some areas are revisited year after year, while others appear on maps only as broad, generalized zones. It explains why scientists sometimes choose indirect observation over direct measurement. And it explains why avoidance is not a sign of ignorance, but a response to the ocean's internal complexity. Depth changes the rules completely. As soon as scientists move beyond the upper layers of the ocean, the rules begin to change. Depth is not just a measure of distance from the surface. It represents a gradual but relentless shift in physical conditions that transforms how the environment behaves and how research must be conducted. The deeper you go, the less the ocean resembles the place most people imagine. Light fades, so temperature stabilizes, pressure increases, and movement takes on a different character. These changes do not occur suddenly. They accumulate steadily, creating a boundary beyond which familiar assumptions no longer apply. And it is beyond this boundary that many of the ocean's most avoided regions begin. Pressure is the first rule change scientists encounter as they descend. With every meter of depth, the weight of the water above increases. At the surface, this pressure is manageable and familiar. But as instruments move downward, the force exerted on them grows rapidly. At depths measured in thousands of meters, the pressure becomes immense, far exceeding anything experienced on land. This pressure does not fluctuate dramatically. It does not surge or retreat. It remains constant, pressing inward from all directions without pause. For equipment, this creates a continuous stress that must be resisted perfectly. Even small weaknesses in design can lead to gradual deformation or sudden failure. Over time, this makes deep regions of the ocean particularly unforgiving places to work. Pressure also changes how materials behave. Metals compress. Seals tighten, flexible components stiffen. Materials that perform reliably at shallow depths may fail silently at greater ones. Scientists must account for these effects when designing instruments. But prediction has limits. Laboratory tests cannot fully replicate the combination of pressure, temperature, and time experienced in the deep ocean. As a result, even well-tested equipment can behave unpredictably once deployed. In regions where pressure is extreme and access is limited, a single failure can end a mission entirely. This risk becomes one of the primary reasons certain deep areas are studied cautiously or indirectly, rather than through long-term, fixed observation. Darkness follows closely behind pressure as depth increases. Sunlight penetrates only a small fraction of the ocean's total depth. Below this illuminated zone lies a vast region where natural light never reaches. In these depths, visual observation becomes dependent on artificial illumination. While cameras and lights allow scientists to see, they introduce new complications. Light can alter behavior, especially in environments where organisms have evolved without it. Some species retreat, others are drawn toward it. Chemical processes can be affected as well. In regions where researchers are trying to understand natural conditions, that the act of observing can change the very system being studied. This limitation becomes more pronounced as the deeper one goes. In shallow waters, light-based observation can be brief and localized. In deeper regions, any sustained study requires continuous illumination, increasing the likelihood of disturbance. For scientists, this creates a dilemma. Data collected under artificial light may not represent undisturbed conditions. In environments where subtle interactions matter, this uncertainty reduces the value of direct observation. As a result, some deep regions are approached with methods that minimize intrusion, even if that means collecting less detailed information. Temperature also behaves differently with depth. Near the surface, ocean temperatures vary widely with weather, season, and latitude. Deeper down, our temperatures become more stable, often hovering just above freezing. This stability might seem like an advantage, but it introduces its own challenges. Cold temperatures affect electronics, batteries, and mechanical systems. Chemical reactions slow. Lubricants thicken. Energy storage becomes less efficient. Instruments designed to operate for long periods must account for these effects. And even then, performance can degrade over time. In regions where maintenance is impossible, this degradation becomes a critical factor in deciding whether long-term deployment is practical. Depth also reshapes movement. At the surface, waves and wind-driven currents dominate. Deeper down, movement is controlled by density differences caused by temperature and salinity. These deep currents move slowly, but they are persistent. They can carry water masses across entire ocean basins over years or decades. For scientists, this slow movement complicates interpretation. Measurements taken at a fixed location may reflect conditions originating far away. Instruments anchored to the seafloor may experience steady drag from currents that are invisible at the surface. Over time, this drag can shift equipment, strain cables, or alter orientation, subtly affecting data quality. In some deep regions, currents interact with the shape of the seafloor, creating turbulence and mixing that are difficult to predict. These interactions can change over time, responding to distant events such as shifts in surface winds or changes in water mass formation elsewhere in the ocean. For researchers attempting to study these processes, consistency becomes elusive. Conditions measured one year may differ significantly the next, not because of local change, but because of distant influences transmitted through the deep circulation system. This interconnectedness adds another layer of uncertainty to deep-sea research. Communication becomes increasingly limited as depth increases. Signals cannot travel directly through seawater over long distances. Data must be transmitted through cables, acoustic signals, or recovered physically by retrieving instruments. Each method has limitations. Cables restrict placement and are vulnerable to damage. Acoustic communication is slow and has limited bandwidth. Physical recovery depends on precise positioning and favorable conditions at the surface. In deep regions far from shore, these challenges multiply. Losing contact with an instrument may mean losing the data permanently. This risk makes some deep environments unattractive for long-term study, even if they are scientifically important. The human element also changes with depth. While scientists do not physically descend into most deep-sea environments, the psychological and operational distance still matters. Missions become more complex. Timelines lengthen, opportunities for correction diminish. When something goes wrong in shallow water, adjustments can often be made quickly. In deep water, decisions must be made carefully and often in advance, with limited feedback once deployment begins. This increases the cost of mistakes and encourages conservative planning. Another consequence of depth is isolation. Deep ocean regions are often far from land, far from infrastructure, and far from alternative options. Research vessels operating in these areas must be self-sufficient. They must carry spare equipment, fuel, and provisions. Weather delays can extend missions unexpectedly. Mechanical issues can force early termination. In these conditions, every decision carries weight. Scientists must choose where to focus their efforts, and depth becomes a major factor in that choice. Regions that combine great depth with other challenges, such as strong currents or unstable seafloor, are often set aside in favor of areas where depth alone is the primary obstacle. Depth also limits the frequency of observation. Shallow regions can be visited repeatedly. Deep regions require specialized vessels, equipment, and planning. Each expedition represents a significant investment. As a result, our deep areas are often sampled infrequently, sometimes years apart. This makes it difficult to detect gradual change or seasonal patterns. Scientists may know what conditions look like at one moment in time, but not how they evolve. Without continuous observation, understanding remains incomplete. This limitation reinforces the tendency to avoid regions where sustained monitoring is impractical. The deep ocean also challenges intuition. Processes occur slowly. Changes unfold over long timescales. Events that matter scientifically may be subtle and easily missed without dense data coverage. In an environment where access is limited and measurements are sparse, distinguishing meaningful patterns from noise becomes difficult. Scientists must decide whether the effort required to reduce this uncertainty is justified by the potential insights gained. In some cases, the answer is yes. In others, resources are directed elsewhere, leaving certain deep regions less explored. It is important to note that avoidance does not imply abandonment. Many deep environments are studied through modeling, indirect measurement, and short-term expeditions. These approaches provide valuable information, but they do not fully replace continuous, in situ observation. The gap between what is desired and what is feasible defines the boundaries of deep-sea research. Depth, more than any other factor, pushes those boundaries outward. As depth increases, challenges do not simply add up, they interact. Pressure affects equipment durability. Darkness affects observation methods. Cold affects power systems. Isolation affects logistics. Together, these factors create environments where even small uncertainties carry large consequences. Scientists are aware of this interaction, and it shapes their choices. Regions where depth amplifies other sources of instability are often approached cautiously or avoided for routine study. Understanding how depth changes the rules helps explain why the ocean remains unevenly studied. It clarifies why knowledge is concentrated in certain layers and regions, while others remain defined by broad generalizations rather than detailed records. Depth transforms the ocean from a place that can be visited into a place that must be negotiated carefully. It demands respect, preparation, and restraint. Pressure, the silent destroyer of technology. Pressure in the ocean does not announce itself, but it does not roar or surge or crash like waves at the surface. It simply exists, increasing steadily with depth, applying force in every direction at once. For scientists, this quiet persistence makes pressure one of the most difficult challenges to work against. Unlike storms or currents, pressure cannot be waited out. It cannot be avoided by choosing a better season. Once an instrument descends past a certain point, pressure becomes an unavoidable condition that must be endured continuously for as long as the equipment remains in place. At relatively shallow depths, pressure is manageable with conventional designs. But as depth increases, the force exerted on every surface becomes immense. Seals must remain perfectly tight. Housings must resist compression without deforming. Any flaw, even one measured in fractions of a millimeter, thus can become a point of failure. Over time, pressure exploits these weaknesses. Materials that appeared stable during testing may begin to fatigue. Components may slowly shift. Microscopic cracks may grow. Often these failures do not happen dramatically. They happen quietly, reducing performance until communication is lost or data quality degrades beyond usefulness. One of the most difficult aspects of pressure-related failure is that it is hard to diagnose from a distance. When an instrument stops transmitting data, Scientists cannot easily determine whether the cause was mechanical failure, power loss, communication interference, or structural collapse. In deep regions, recovery is often impossible. The equipment may lie thousands of meters below the surface, beyond the reach of standard retrieval methods. Or even when recovery is theoretically possible, the cost and complexity may be too great to justify an attempt. This uncertainty makes deep, high-pressure environments particularly risky for long-term study. Pressure also changes how materials age. Metals under constant compression behave differently than they do at the surface. Plastics may become brittle. Elastic components may lose flexibility. Adhesives can weaken. These effects accumulate slowly, making it difficult to predict how long an instrument will function reliably. Engineers can design for pressure resistance, but design margins are never infinite. In regions where pressure is extreme and access is limited, the margin for error becomes uncomfortably small. Power systems are especially vulnerable. Batteries are affected by pressure both directly and indirectly. Casings must withstand compression without leaking. Chemical reactions inside batteries can slow in cold, high-pressure environments. If a power system fails, the instrument becomes silent, regardless of whether other components remain intact. In deep ocean regions, this silence often marks the end of a dataset. Scientists may wait months or years for a scheduled recovery that never delivers usable information. Over time, these experiences influence where researchers choose to deploy their most valuable equipment. Pressure also complicates sensor calibration. Many instruments are calibrated at or near the surface, then adjusted mathematically to account for expected changes at depth. But pressure can affect sensors in subtle ways that are difficult to model precisely. Readings may drift. Sensitivity may change. What appears to be a real environmental signal may, in fact, be an artifact of pressure-induced distortion. In stable environments, these effects can sometimes be corrected through comparison and repetition. In unstable or rarely visited regions, uncertainty remains. Scientists must decide whether the data they collect can be trusted, and in some cases, the answer is not clear. The cumulative cost of pressure-related failure is significant. Deep-sea instruments are expensive to design, build, and deploy. Ship time is costly. Personnel and logistics add further expense. When equipment fails due to pressure, the loss is not limited to the hardware itself. It includes lost data, missed opportunities, and delays in research progress. Funding agencies and research institutions are acutely aware of these risks. Over time, this awareness shapes priorities. Regions where pressure consistently undermines reliability may be studied indirectly or less frequently, not because they lack importance, but because sustained observation remains impractical. Pressure also limits human involvement. While most deep-sea research relies on unmanned systems, human-occupied vehicles still play a role in certain investigations. These vehicles face the same challenges as instruments, multiplied by the need to protect human life. Safety margins must be larger. Designs must be more conservative. Operating windows become narrower. As depth increases, the number of vehicles capable of safe operation decreases. This further restricts access to the deepest regions and reinforces the tendency to avoid them for routine study. Another consequence of pressure is time dependency. An instrument that functions correctly for a short deployment may fail during a longer one. Pressure-related fatigue accumulates over weeks and months. This makes long-term monitoring especially difficult in deep regions. Scientists may be able to collect snapshots of data, but continuous records remain rare. Without long-term data, understanding change becomes difficult. Patterns may be missed. Trends may remain hidden. This limitation contributes to the uneven distribution of knowledge across the ocean. Pressure also interacts with other factors, amplifying their effects. In cold environments, pressure worsens the performance of power systems. In turbulent regions, pressure stresses components already under mechanical strain. In chemically active zones, pressure can influence corrosion rates. These interactions create environments where multiple challenges overlap, increasing the likelihood of failure. Scientists recognize these compounded risks and factor them into their planning. Areas where pressure combines with other destabilizing forces often become candidates for avoidance. Despite advances in technology, pressure remains a fundamental constraint. New materials, improved designs, and better testing have expanded the range of depths that can be explored. Autonomous vehicles can descend deeper than ever before. Sensors can operate under greater loads. But the underlying reality has not changed. Pressure increases predictably, relentlessly, and without regard for human ambition. It sets a boundary that technology can approach, but never eliminate. Understanding pressure as a limiting force helps explain why some parts of the ocean remain lightly studied. It is not because scientists lack curiosity or capability. It is because pressure imposes costs that extend beyond engineering challenges. It affects reliability, safety, budget, and data quality. In regions where these costs outweigh what can reasonably be gained, restraint becomes the responsible choice. Darkness and the limits of observation. As depth increases, light fades gradually and then disappears entirely. This transition is not abrupt. Sunlight weakens meter by meter, losing color first, then brightness, until finally there is nothing left but darkness. Below a certain depth, the ocean exists in a state of permanent night. No sunrise, no sunset, no natural illumination of any kind. For scientists, with this absence of light fundamentally changes how the environment can be observed, measured, and understood. Darkness does not simply make research more difficult. It reshapes the methods available and limits what can be known with confidence. In the upper ocean, light allows direct observation. Cameras can record natural behavior. Visual surveys can identify organisms, structures, and patterns. Even when instruments are used, they are supported by what researchers can see. In darkness, this visual foundation disappears. Any attempt to observe must rely on artificial light, and artificial light comes with consequences. It introduces energy into a system that evolved without it. It changes behavior. It alters movement. It can trigger responses that would never occur under natural conditions. This makes darkness not just an absence of visibility, but a source of uncertainty. Many deep-sea organisms are adapted to extreme low-light environments. Some have sensitive eyes tuned to bioluminescence. Others avoid light entirely. When illuminated by research equipment, these organisms may retreat, freeze, or move unpredictably. What scientists record in those moments may not represent normal behavior. It may reflect stress, confusion, or avoidance. Over time, this raises an important question. If observation changes the system, how accurately can it be studied? In regions where this uncertainty is high, scientists must limit how often and how intensely they observe, which reduces data availability. Darkness also affects navigation and positioning. In shallow water, visual cues help guide instruments and vehicles. Landmarks can be identified. Terrain can be assessed in real time. In deep, dark regions, navigation depends entirely on sensors, sonar, and pre-programmed paths. These systems work well under stable conditions, but they are not infallible. Errors in positioning can accumulate. Vehicles may drift off course. Instruments may be deployed slightly outside the intended study area. When this happens in darkness, detection is delayed. Scientists may not realize an error has occurred until data is analyzed later, long after correction is possible. The lack of light also limits context. A single sensor reading in darkness provides information about a specific point, but not about its surroundings. Without visual reference, it can be difficult to determine whether a measurement reflects local conditions or a broader pattern. Cameras can provide some context, but only within the narrow field illuminated by artificial light. Beyond that, the environment remains unknown. This fragmentation of information makes it harder to build a complete picture of how a region behaves, especially over time. Darkness further complicates long-term monitoring. Instruments left in place for months or years must operate without visual verification. Scientists cannot easily check whether a sensor has shifted, become buried, or been obstructed. They must rely on indirect signals, such as changes in data patterns or communication strength, to infer problems. In stable environments, these inferences can be reliable. In dynamic or complex regions, they may not be. This uncertainty increases the risk of collecting data that is incomplete or misleading. Biological processes in darkness also behave differently. Without sunlight, primary production relies on chemical energy rather than photosynthesis. Food webs are structured around scarcity. Growth rates are slow. Recovery from disturbance can take decades. In these conditions, even minor interference can have long-lasting effects. Scientists are aware of this sensitivity, and in some regions, they deliberately limit activity to avoid altering fragile systems. Darkness, in this sense, is not just a physical condition, but an ecological one that demands caution. Darkness also affects chemistry. Many chemical reactions in the ocean are influenced by light. In its absence, different pathways dominate. Measuring these processes requires specialized sensors and careful calibration. Data collected under artificial light may not reflect natural conditions. In regions where chemical gradients are subtle, this can make interpretation difficult. Scientists must weigh whether the information gained is worth the uncertainty introduced by observation. Another challenge introduced by darkness is time. Without natural light cycles, it becomes harder to link processes to daily rhythms. Biological activity may still follow internal clocks, but detecting these patterns requires continuous monitoring. Continuous monitoring in deep, dark regions is expensive and technically demanding. Instruments must operate reliably for long periods without maintenance. Any failure may go unnoticed until recovery, if recovery is possible at all. This risk limits how often such deployments are attempted. Darkness also magnifies the consequences of error. A misplaced instrument in a well-lit environment can often be located and corrected. In darkness, errors persist unseen. A sensor angled incorrectly may collect biased data for months. A camera partially obstructed may miss key observations entirely. These issues do not announce themselves. They hide within the data, revealing themselves only through careful analysis, if at all. In regions where errors are difficult to detect and correct, scientists become cautious about deploying equipment in the first place. Technological advances have reduced some of these limitations. Low-light cameras, sensitive sensors, and autonomous systems have expanded what can be observed in darkness. But these tools do not eliminate the fundamental problem. Observation still requires interaction. Interaction still changes conditions, and darkness still limits context. As a result, some deep, dark regions of the ocean remain lightly studied, not because they are unreachable, but because reliable observation remains difficult to achieve. Darkness also interacts with other challenges. Combined with pressure, it limits design options. Combined with cold, it strains power systems. Combined with isolation, it reduces opportunities for correction. In regions where darkness overlaps with strong currents, unstable seafloor, or chemical activity, the difficulty multiplies. These overlapping factors define many of the ocean's avoided zones. Places where darkness does not exist alone, but reinforces other sources of uncertainty. Understanding the role of darkness helps explain why scientific knowledge of the ocean is uneven. It clarifies why some regions are described in detail, while others are known only in general terms. Darkness creates environments where observation is possible, but never simple. Where data can be collected, but never without compromise. Where restraint becomes part of responsible science. Ocean currents that never truly rest. Even in the deepest, darkest parts of the ocean, nothing is ever completely still. While the surface may appear calm and unmoving, beneath it water is constantly in motion. Sliding, rotating, sinking, rising, and flowing along invisible pathways shaped by temperature, salinity, and the contours of the seafloor. These movements are known collectively as ocean currents, and they form one of the most persistent challenges scientists face when studying certain regions of the sea. Currents do not stop, and they do not pause for observation. And in many parts of the ocean, they make stability impossible. At the surface, currents are easier to recognize. They are influenced by wind, storms, and the rotation of the Earth. They shift with seasons and weather systems, and they can often be predicted with reasonable accuracy. Ships account for them in navigation. Satellites track their broad patterns. But beneath the surface, currents behave differently. They are driven not by wind, but by differences in density caused by temperature and salinity. These deep currents move slowly, but they are powerful in their persistence. Once established, they can flow steadily for years, carrying vast volumes of water across entire ocean basins. For scientists, this persistent movement creates a fundamental problem. Many research methods assume a degree of stability. Instruments are deployed with the expectation that they will remain in roughly the same position. Sensors are calibrated based on local conditions. Data is interpreted under the assumption that measurements reflect a particular region. But in areas dominated by strong or variable currents, these assumptions break down. Instruments drift, anchors drag, cables stretch and sway. Over time, equipment may end up far from its intended location, collecting data that no longer represents the target environment. This drifting is not always dramatic. Often, it happens slowly and quietly. An instrument might move a few meters each day, carried by currents that are invisible from the surface. Over weeks or months, that movement can add up to kilometers. When scientists finally recover the equipment, they may discover that the data reflects a path rather than a place. Interpreting such data becomes difficult. Was a change in measurement caused by environmental variation or by the instrument moving into a different water mass? In regions where currents are strong and complex, this question can be impossible to answer with confidence. Currents also complicate the deployment and recovery of equipment. Lowering instruments through moving water requires precise control. Even slight miscalculations can cause cables to tangle or sensors to strike the seafloor at the wrong angle. In calm regions, these risks are manageable. In areas with strong currents, they increase sharply. Recovery can be even more challenging. Equipment may no longer be where it was deployed. Acoustic signals used to locate instruments can be distorted by water movement. Time spent searching increases fuel use and reduces the overall productivity of an expedition. In some cases, instruments are simply lost. Another challenge arises from the way currents interact with the sea floor. As water flows over underwater ridges, slopes, and valleys, it accelerates, slows, and changes direction. These interactions create turbulence. mixing layers of water that might otherwise remain separate. While this mixing is scientifically important, it influences nutrient transport, heat distribution, and ecosystem dynamics. It also introduces unpredictability. Conditions can change rapidly over short distances. A sensor deployed in one spot may experience very different conditions than a sensor just a short distance away. This spatial variability makes it difficult to generalize findings and discourages long-term deployment in especially dynamic regions. Boundary zones where different currents meet are particularly challenging. In these areas, water masses with different temperatures and salinity collide and slide past one another. The boundaries between them are not fixed. They shift with seasons, weather, and distant changes in circulation. These shifting boundaries can pass over instruments repeatedly, altering measurements in ways that are difficult to interpret. Scientists value data from such regions because they play a key role in global ocean circulation. But the very processes that make them important also make them difficult to study consistently. Currents also influence biological processes, further complicating research. Many marine organisms rely on currents to transport nutrients, larvae, and food. As currents change, so do biological distributions. Species may appear or disappear from a region over short timescales. For scientists studying ecosystems, this movement creates uncertainty. Is a change in population caused by environmental stress or simply by a shift in current patterns? In regions where currents dominate, answering this question requires dense, long-term data that is difficult to collect. The vertical movement of water adds another layer of complexity. Currents do not only flow horizontally. In many parts of the ocean, water rises from depth or sinks from the surface in processes known as upwelling and downwelling. These vertical motions bring cold, nutrient-rich water upward or carry surface water downward. They can change local conditions rapidly, affecting temperature, chemistry, and biological activity. Instruments designed to measure a stable environment may suddenly find themselves in a completely different one. In regions where vertical movement is strong and unpredictable, maintaining consistent measurements becomes extremely challenging. For long-term monitoring, currents present a particularly stubborn obstacle. Fixed observation stations are most effective in relatively stable environments. In regions with strong currents, maintaining a fixed position requires heavy anchors and reinforced structures, which increase cost and complexity. Even then, movement cannot be eliminated entirely. Over time, strain accumulates. Components wear. Failure becomes more likely. Scientists must decide whether the benefits of long-term data justify these risks. In many cases, they choose locations where currents are weaker or more predictable, leaving highly dynamic regions less studied. Currents also interact with weather at the surface. Storms can strengthen surface currents, which in turn influence deeper layers. These changes propagate downward, altering conditions at depth days or even weeks later. This delayed response makes planning difficult. An area that appears suitable for deployment based on current conditions may become unstable later due to events far away. Scientists tracking these changes must account for influences that extend beyond the immediate region, adding complexity to both observation and interpretation. Another consequence of constant movement is energy demand. Instruments operating in moving water require more power to maintain position, transmit data, or stabilize orientation. Power systems must compensate for drag and vibration. In deep or remote regions, where replacing batteries is impractical, increased power demand shortens operational life. This limits the duration of deployments and reduces data continuity. Regions with especially strong currents often see higher failure rates simply because equipment is forced to work harder under more stressful conditions. The psychological impact of currents also plays a role, particularly during crewed operations. Scientists and technicians working on vessels must contend with continuous motion. Equipment handling becomes more difficult. Precision tasks take longer. Fatigue accumulates. While these challenges may seem secondary, they influence safety and efficiency. In areas where currents create persistent motion and instability, operations become more demanding, increasing the likelihood of error. Over time, these experiences inform decisions about where future missions are planned. Despite these challenges, scientists do study currents extensively, using satellites, drifting buoys, and autonomous vehicles. These tools provide valuable information, but they also highlight the limits of direct observation. Drifting instruments, by definition, move with the water, making it difficult to isolate local conditions. Autonomous vehicles can follow programmed paths, but they are still subject to the forces around them. In regions where currents dominate, control is always partial. This reality reinforces the idea that some parts of the ocean resist being pinned down and measured in the ways scientists prefer. Understanding the role of currents helps explain why avoidance is often selective rather than absolute. Scientists may sample a dynamic region briefly, then withdraw. They may rely on indirect measurements rather than fixed installations. They may focus on edges rather than centers, where conditions are slightly more stable. These choices are not signs of weakness or lack of interest. They are adaptations to an environment that refuses to hold still. Vertical motion, upwelling, downwelling, and constant mixing. When people imagine movement in the ocean, they usually picture water flowing sideways, carried by currents across the surface or along the sea floor. But some of the most influential motion in the sea happens vertically. Water rises, water sinks, layers mix and separate again. These vertical movements are quieter than surface waves and slower than major currents, but they have profound effects on the ocean environment. For scientists, vertical motion introduces a level of instability that makes certain regions difficult to study consistently and explains why some areas are approached with caution or avoided altogether. Upwelling is one of the most important vertical processes in the ocean. It occurs when deep, cold, nutrient-rich water rises toward the surface, replacing warmer surface water that has been pushed away by wind or current patterns. From a scientific perspective, upwelling zones are incredibly valuable. They support productive ecosystems, influence fisheries, and play a role in regulating climate by moving heat and carbon through the ocean. But they are also some of the most variable environments in the sea. Conditions can change rapidly as deep water reaches the surface, altering temperature, chemistry, and biological activity over short periods of time. This variability creates a challenge for observation. Instruments deployed in an upwelling region may record sharp shifts in conditions that are difficult to interpret. A sudden drop in temperature might reflect a genuine environmental change, or it might simply mean that deeper water has temporarily risen into the measurement zone. Without dense, repeated measurements across depth and time, distinguishing between these possibilities is difficult. In regions where upwelling is frequent and unpredictable, these scientists may collect data that is rich but fragmented, making long-term trends hard to identify. Downwelling, the opposite process, also complicates research. In downwelling zones, surface water sinks, carrying heat, oxygen, and dissolved substances into deeper layers. This process can suppress biological activity at the surface, while altering conditions at depth. For scientists studying deep environments, downwelling introduces uncertainty about the origin of the water being measured. Is it local, or has it traveled from far away? Has it recently been in contact with the atmosphere, or has it been isolated for decades? These questions matter, but answering them requires extensive sampling that is difficult to achieve in remote or unstable regions. Vertical mixing adds another layer of complexity. In many parts of the ocean, the layers of water with different temperatures and salinity are separated by boundaries that resist mixing. But in other regions, these boundaries break down. Wind, tides, seafloor features, and currents can stir the water column, blending layers that would otherwise remain distinct. This mixing can occur sporadically or continuously, depending on local conditions. For scientists, mixing complicates the interpretation of data. Measurements taken at a single depth may reflect influences from above or below, blurring the distinction between environments. Regions where strong mixing occurs are often scientifically important. They influence how heat and nutrients are distributed, how ecosystems function, and how the ocean responds to external forces. But they are also difficult places to study. Instruments designed to measure stable layers may encounter constantly shifting conditions. Sensors may record signals that fluctuate widely, making it hard to determine what represents a baseline. In these environments, long-term consistency is rare, and without consistency, understanding becomes uncertain. Vertical motion also affects the physical stability of equipment. Rising and sinking water creates forces that act on instruments from multiple directions. Moorings designed to hold sensors at fixed depths may be stretched or compressed as water moves past them. Over time, this motion can cause wear, alter positioning, or lead to failure. In regions with strong vertical movement, maintaining precise depth control becomes challenging. Even small deviations can influence data quality, particularly when studying processes that vary sharply with depth. Another complication introduced by vertical motion is timing. Upwelling and mixing often occur in pulses rather than steady flows. They may be triggered by changes in wind, tides, or distant weather events. These triggers are not always predictable. Scientists planning fieldwork may arrive during a quiet period, only to see conditions change dramatically days later. Alternatively, they may miss key events entirely if their observation window is too short. This unpredictability makes it difficult to design experiments that capture the full range of behavior in these regions. Vertical motion also influences chemical processes in the ocean. When deep water rises, it can bring low oxygen or high carbon conditions to shallower depths. This affects organisms and alters chemical balances. Instruments measuring these changes must be carefully calibrated and interpreted. In regions where vertical motion is frequent, distinguishing between local chemical reactions and transported signals becomes difficult. Scientists must decide whether the complexity of the environment allows for clear conclusions or whether the uncertainty is too great for reliable analysis. Biological responses to vertical motion further complicate research. Many marine organisms track changes in temperature and nutrient availability, moving up or down in the water column as conditions shift. In upwelling zones, sudden increases in nutrients can trigger blooms that appear and disappear quickly. In mixing regions, organisms may be redistributed in ways that obscure long-term patterns. For scientists studying ecosystems, these rapid changes make it hard to separate natural variability from longer-term trends. The interaction between vertical motion and other ocean processes amplifies difficulty. In regions where strong currents, complex seafloor features, and variable weather coincide, vertical movement becomes more intense and less predictable. These overlapping challenges define some of the most avoided areas of the ocean. not because they are uninteresting, but because they resist sustained, controlled observation. Despite these challenges, scientists continue to study vertical motion using a combination of tools. Profiling floats, autonomous vehicles, and satellite data provide valuable insights. But these methods often capture snapshots rather than continuous records. In regions where vertical motion dominates, the gap between what is observed and what is understood remains wide. Filling that gap would require long-term, high-resolution monitoring that is difficult to maintain in such dynamic environments. Understanding vertical motion helps explain why some ocean regions remain less studied than others. It reveals how movement that cannot be seen from the surface can shape the environment in profound ways. It also highlights the limits of current research methods when faced with constant change. In the ocean, stability is rare, and vertical motion ensures that some places never settle long enough to be measured with confidence. The unstable seafloor beneath the ocean. From the surface, the ocean appears flat and uniform, giving the impression that the ground beneath it must be solid and unchanging. But the seafloor is not a fixed foundation. In many parts of the ocean, it is soft, fractured, sloped, or slowly shifting. Unlike land, where movement can often be seen or measured directly, changes on the seafloor happen out of sight, hidden beneath thousands of meters of water. For scientists, this hidden instability creates serious challenges and explains why certain regions of the ocean remain difficult to study safely and consistently. Much of the seafloor is covered in sediment rather than solid rock. Fine particles settle slowly from the surface over thousands of years, forming thick layers that can behave more like mud than stone. These sediments may appear stable, but they can shift under pressure, vibration, or changes in water movement. Instruments anchored into this material may slowly sink, tilt, or become buried. Over time, the sensors that were carefully positioned can end up misaligned or completely obstructed. When this happens in deep or remote regions, scientists often have no way to correct the problem. Slopes on the seafloor add another layer of risk. Continental margins, underwater ridges, and deep-sea canyons create steep terrain that is prone to movement. Gravity acts on these slopes continuously, and small disturbances can trigger larger shifts. Submarine landslides, though rarely observed directly, are known to occur and can move enormous amounts of material in a short time. These events can bury instruments, sever cables, or alter the local environment completely. In regions where slope failure is more likely, long-term deployment becomes a gamble rather than a guarantee. Earthquakes beneath the ocean also contribute to seafloor instability. Tectonic activity can cause sudden movement, fracturing sediment layers and reshaping the terrain. Even when earthquakes are small, their effects can travel through soft sediments, destabilizing areas that were previously calm. For researchers, this means that a site considered safe during planning may change without warning. Instruments designed for stationary conditions may be damaged or displaced, and the resulting data may be difficult or impossible to interpret. The seafloor is also shaped by slow processes that are harder to detect. Over time, currents can erode sediment, exposing harder layers or creating uneven surfaces. Chemical reactions between seawater and sediment can alter material strength. Gas trapped beneath the seafloor may migrate slowly, weakening overlying layers. These changes happen quietly, without dramatic signals. Yet their effects can be significant, altering the stability of an area over months or years. Scientists attempting long-term observation in such regions must accept a high degree of uncertainty. Another challenge arises from the uneven nature of the seafloor itself. Unlike land, which often offers relatively flat areas for construction and deployment, the ocean floor can be highly irregular. Rocks, ridges, depressions, and soft patches may exist within a small area. Mapping this terrain in detail requires time and specialized equipment, and even high-resolution maps may miss subtle features. An instrument placed on what appears to be a stable surface may actually rest on a fragile layer that shifts over time. When this happens far from shore, recovery and adjustment are rarely possible. And sea floor instability also complicates the use of cables and moorings. Many ocean research systems rely on cables to transmit data or hold equipment in place. These cables must rest on or near the seafloor, where they are exposed to movement, abrasion, and burial. In unstable regions, cables can be damaged or broken, cutting off communication entirely. Repairing such damage requires locating the break, deploying specialized vessels, and operating in conditions that may still be changing. In some regions, the risk of repeated failure discourages permanent installations altogether. Biological activity can further influence seafloor conditions. Burrowing organisms disturb sediment as they move and feed. Large animals may displace material or interact with equipment. Over time, these biological processes can alter the local environment enough to affect instrument stability. While these changes are usually gradual, their cumulative effect can be significant, particularly in areas where sediments are already soft or loosely packed. The combination of physical, chemical, and biological processes makes the seafloor a dynamic environment rather than a static base. For scientists, this means that assumptions about stability must be treated cautiously. A site that appears suitable during initial surveys may become unreliable over time. This uncertainty increases the cost and complexity of research and encourages scientists to favor regions where the seafloor is more predictable. In some cases, scientists choose to study unstable seafloor regions using short-term missions rather than long-term installations. And brief visits allow for data collection without committing equipment to an environment that may change unexpectedly. While this approach yields valuable information, it does not provide the continuous records needed to understand long-term processes. As a result, knowledge of these regions remains incomplete. The unstable nature of the seafloor also influences safety considerations. While most deep-sea research is conducted remotely, the risk of equipment failure still affects human decision-making. Lost instruments represent lost investment and lost opportunity. When failure becomes likely rather than occasional, planners must reconsider whether a site is suitable for study. Over time, regions with a history of instability develop a reputation for being difficult, shaping future research choices. Understanding the seafloor as an active, but changing environment helps explain why some parts of the ocean remain lightly studied. It reveals that avoidance is not driven by ignorance, but by experience. Scientists know that reliable data depends on stable conditions, and where the ground itself refuses to remain still, stability is hard to achieve. Tectonic boundaries beneath the ocean. Beneath much of the world's oceans, the Earth's surface is slowly but constantly in motion. Massive tectonic plates slide past one another, pull apart, or collide deep below the water, reshaping the seafloor over timescales that range from sudden and violent to slow and almost imperceptible. These tectonic boundaries form some of the most dynamic regions on the planet. They are also among the most challenging environments for scientists to study consistently, which is why many of them remain lightly monitored or are approached only for short periods of time. Mid-ocean ridges are one of the most prominent examples of tectonic activity beneath the sea. These long, underwater mountain chains mark places where tectonic plates are moving apart and new seafloor is being created. Magma rises from below, cools, and solidifies, gradually adding material to the ocean floor. From a scientific perspective, these regions are incredibly important. They help explain how the Earth renews its surface, and how heat moves from the planet's interior into the ocean. But they are also unstable environments. The ground is fractured, uneven, and constantly adjusting. Small earthquakes are common. Temperature and chemistry can change abruptly over short distances. For long-term instruments, this instability creates persistent risk. Subduction zones present a different set of challenges. In these regions, one tectonic plate slides beneath another, descending into the Earth's mantle. This process creates deep ocean trenches and some of the most extreme pressure conditions on the planet. Subduction zones are also associated with powerful earthquakes and sudden seafloor movement. Even when earthquakes are not immediately destructive, they can shift sediment, alter slopes, and destabilize equipment. Scientists studying these areas must account for the possibility that a carefully chosen site may change dramatically without warning. Fault lines beneath the ocean add another layer of complexity. These fractures allow plates to slide past one another horizontally, releasing stress in bursts. While many of these movements are small, their cumulative effect can reshape the seafloor over time. Instruments placed near faults may experience vibration, tilting, or gradual displacement. These changes may not be obvious in real time, especially in deep, dark environments. When data anomalies appear later, it can be difficult to determine whether they reflect true environmental signals or subtle shifts caused by tectonic motion. Tectonic regions also influence fluid movement beneath the seafloor. Cracks and fractures allow water to circulate through rock, altering temperature and chemistry. This circulation can change over time as fractures open or close. For scientists measuring chemical processes, these changes introduce uncertainty. A sensor deployed in one location may suddenly encounter different conditions as subsurface pathways shift. Without direct access to the source of these changes, interpretation becomes difficult. Another challenge in tectonic zones is heat. Areas near plate boundaries often experience elevated heat flow from the Earth's interior. This heat can affect surrounding water and sediment, influencing both physical and chemical processes. Instruments designed for cold, stable environments may struggle under these conditions. Components may degrade faster. Calibration may drift. Power systems may be stressed. In regions where heat varies unpredictably, maintaining reliable measurements becomes increasingly difficult. The seafloor terrain in tectonic zones is often highly irregular. Ridges, valleys, cracks, and steep slopes can exist within a small area. Mapping this terrain in sufficient detail to support instrument deployment requires time and repeated surveys. Even then, subtle features may be missed. An instrument placed on what appears to be a stable platform may rest on fractured rock that shifts over time. When this happens far below the surface, correction is rarely possible. Tectonic activity also affects the broader ocean environment. Earthquakes can trigger submarine landslides, which disturb sediment and alter water chemistry. These disturbances can propagate outward, affecting regions far from the original event. Scientists attempting to monitor long-term trends may find their data interrupted by sudden changes that are difficult to separate from gradual processes. In areas where tectonic events are frequent, these interruptions make it hard to build continuous records. Safety considerations further influence research decisions in tectonic zones. While most deep sea work is conducted remotely, the risk of equipment loss remains high. Instruments damaged by seismic activity may be unrecoverable. Repair missions may be delayed by the same instability that caused the failure. Over time, repeated losses can make sustained study financially impractical. Research programs must weigh the scientific value of these regions against the likelihood of failure. Despite these challenges, tectonic regions are not ignored. Scientists study them using targeted expeditions, short-term deployments, and indirect measurements. These approaches provide valuable insights without committing resources to environments that resist long-term occupation. However, this strategy also means that data from tectonic zones is often episodic rather than continuous. Important changes may occur between observations, leaving gaps in understanding. Tectonic boundaries beneath the ocean illustrate a broader theme that runs through this documentary. The most active and informative regions of the sea are often the least cooperative. Their constant motion makes them difficult to measure with the consistency science requires. Avoidance, in this context, is not about retreat. It is about recognizing where stability is unlikely and adjusting methods accordingly. Volcanic regions beneath the ocean. Hidden beneath thousands of meters of water, vast portions of the ocean floor are shaped by volcanic activity. These regions do not resemble the dramatic eruptions people associate with volcanoes on land. There are no towering plumes of ash rising into the sky, no glowing rivers of lava visible from a distance. Instead, volcanic processes beneath the sea unfold quietly, often without obvious surface signs. Yet, despite this apparent calm, these environments are among the most unstable and demanding places scientists attempt to study, and they remain some of the most carefully approached areas of the ocean. Underwater volcanoes, often called seamounts, are scattered across the ocean floor. Some rise thousands of meters above the surrounding seabed, while others remain hidden beneath deep water, their presence known only through sonar mapping. These structures influence ocean circulation, biological communities, and chemical exchange. They can create localized currents, redirect water flow, and serve as habitats for unique ecosystems. From a scientific perspective, they are valuable natural laboratories, but their very nature makes them difficult to observe safely and consistently. One of the defining characteristics of volcanic regions is heat. Even when an underwater volcano is not actively erupting, heat from below the Earth's crust can warm surrounding rock and water. This heat does not spread evenly. It moves through fractures and porous layers, creating patches of warmer water in otherwise cold environments. For instruments designed to operate in stable, near-freezing conditions, these temperature variations can be problematic. Sensors may drift out of calibration. Power systems may behave unpredictably. Components exposed to repeated heating and cooling cycles may degrade faster than expected. Volcanic regions are also chemically complex. Fluids released from beneath the seafloor can contain dissolved metals, gases, and minerals that alter the surrounding water chemistry. These changes can occur gradually or suddenly, depending on subsurface activity. Instruments measuring chemical properties must be carefully calibrated to distinguish between background conditions and volcanic influence. In regions where chemistry fluctuates unpredictably, data interpretation becomes difficult. Scientists may struggle to determine whether observed changes represent long-term trends or short-lived volcanic events. Another challenge is structural instability. Volcanic terrain is often fractured and uneven. Lava flows create rough surfaces. Collapsed structures form steep slopes and irregular cavities. These features make it difficult to place instruments securely. Equipment deployed on volcanic seafloor may rest on unstable ground that shifts over time. Small collapses or changes in pressure can alter positioning, affecting data quality. In deep water, these changes often go unnoticed until instruments are recovered, if they are recovered at all. Volcanic activity beneath the ocean is not always predictable. Some regions remain quiet for long periods, then become active with little warning. Even minor eruptions or magma movements can alter local conditions dramatically. Heat output may increase. Chemical release may intensify. Seafloor structures may crack or collapse. For long-term monitoring, this unpredictability presents a serious challenge. Instruments designed to record gradual change may be overwhelmed or damaged by sudden events. When failure occurs, replacing equipment in such regions is costly and risky. Volcanic regions also interact with surrounding water movement. Heat released from below can drive convection, creating localized currents that rise and spread outward. These currents can carry altered water masses away from the source, affecting areas far beyond the volcanic site. Instruments deployed nearby may record signals influenced by volcanic activity without being directly adjacent to it. This complicates interpretation. Scientists must consider whether changes observed at a given location originate locally or are transported from elsewhere. Biological communities in volcanic regions add another layer of complexity. Some organisms thrive in these environments, relying on chemical energy rather than sunlight. These ecosystems are often fragile and slow-growing. Disturbance from scientific activity can have long-lasting effects. Scientists are aware of this sensitivity and often limit how much equipment they deploy or how long they remain in such areas. Ethical considerations, combined with operational risk, contribute to cautious approaches and limited study. The combination of heat, chemical variability, uneven terrain, and biological sensitivity makes volcanic regions demanding places to work. Even when scientists succeed in collecting data, maintaining long-term observation is difficult. Instruments may fail sooner than expected. Conditions may change faster than anticipated. Data continuity may be broken. Over time, these challenges reinforce the perception of volcanic regions as high-risk environments, where avoidance is sometimes the most practical option. This does not mean volcanic regions are ignored. Scientists continue to explore them using short expeditions, autonomous vehicles, and targeted sampling. These methods provide valuable insights without committing resources to prolonged deployment. However, this approach also means that observations are often episodic. Important changes may occur between visits, leaving gaps in understanding. These gaps persist not because scientists lack interest, but because the environment resists sustained presence. Volcanic regions beneath the ocean illustrate a broader pattern seen throughout the sea. Areas defined by constant change, hidden instability, and unpredictable forces demand a level of adaptability that stretches current technology and resources. Scientists must decide where to focus their efforts, balancing curiosity with practicality. And in many cases, volcanic regions remain on the edge of what is possible, studied carefully but not continuously. Hydrothermal vent zones, heat, chemistry, and fragile balance. Deep beneath the ocean's surface, in regions where the Earth's crust is thin and fractured, seawater circulates through hot rock, becomes chemically altered, and rises back into the ocean through openings known as hydrothermal vents. These places are among the most extraordinary environments on the planet. They support life without sunlight, driven instead by chemical energy released from the Earth itself. For scientists, hydrothermal vents offer rare insight into biology, chemistry, and geology. Yet they are also among the most carefully approached and selectively studied regions of the ocean, not because they are inaccessible, but because their conditions resist long-term stability. Hydrothermal vent systems exist in environments defined by extremes. Water emerging from vents can be far hotter than the surrounding deep ocean, carrying dissolved metals, gases, and minerals. This hot fluid mixes rapidly with cold seawater, creating sharp chemical and temperature gradients over very small distances. Instruments placed only a few meters apart may record completely different conditions. for scientists attempting to build consistent data sets. This variability presents a challenge. Measurements taken at one moment may not reflect conditions even minutes later. The chemistry of vent fluids is complex and often harsh. High concentrations of dissolved metals and reduced compounds can corrode equipment, clog sensors, and interfere with measurements. Instruments designed for stable deep-sea conditions may degrade quickly when exposed to vent chemistry. Over time, sensors may lose sensitivity or fail entirely. This makes long-term deployment difficult and increases the cost of repeated sampling. Scientists must often choose between collecting brief snapshots of data or risking equipment loss in an environment that changes without warning. Hydrothermal vents are also geologically unstable. They form along fractures and faults that can shift as tectonic forces act on the seafloor. New vents may open while existing ones close. Flow rates can change as subsurface pathways evolve. A vent that appears active during one expedition may be quiet during the next. This unpredictability complicates planning. Instruments placed to monitor a specific vent may end up observing an inactive site, while new activity occurs elsewhere, beyond reach. Maintaining continuous observation in such a dynamic setting is rarely practical. Heat adds another layer of difficulty. Vent fluids can reach temperatures high enough to damage electronics and structural components. Even when instruments are placed at a distance, fluctuating heat can affect performance. Repeated exposure to thermal stress can weaken materials, shorten battery life, and cause calibration drift. Designing equipment to withstand these conditions requires significant resources. And even then, durability cannot be guaranteed. Biological communities around hydrothermal vents are both resilient and fragile. Many organisms thrive in these extreme environments, relying on chemical energy rather than sunlight. Yet these ecosystems are finely balanced. Changes in fluid flow or chemistry can alter community structure. Disturbance from scientific activity, such as repeated visits or equipment placement, can have lasting effects. Scientists are acutely aware of this sensitivity and often limit how much interaction occurs at vent sites. Ethical considerations play a role alongside technical challenges in shaping cautious research strategies. Observation itself can influence vent environments. Artificial light, physical contact, and changes in water flow caused by equipment can alter conditions. In systems where gradients are sharp and organisms are specialized, even small disturbances matter. This makes it difficult to observe without influencing what is being observed. Scientists must constantly weigh the value of detailed data against the risk of altering the system they are studying. The remoteness of vent sites further complicates research. Most hydrothermal vents lie in deep ocean regions far from land. Reaching them requires specialized vessels, submersibles, or autonomous vehicles. Ship time is expensive, and weather constraints limit operational windows. Each expedition must be carefully planned, and opportunities for follow-up visits may be years apart. This spacing between observations leaves gaps in data and limits understanding of long-term changes. Because of these challenges, hydrothermal vents are often studied through targeted expeditions rather than continuous monitoring. Scientists may collect samples, deploy short-term instruments, and then withdraw. While this approach yields valuable insights, it does not provide a complete picture of how vent systems evolve over time. Important transitions may occur between visits, unseen and unrecorded. Hydrothermal vent zones illustrate a broader principle seen throughout the ocean. The environments that offer the most unique information are often those that resist sustained observation. Their extreme conditions demand caution, patience, and restraint. Avoidance, in this context, does not mean turning away from discovery. It means acknowledging limits and adapting methods to respect an environment that operates on its own terms. Biological complexity and fragile deep sea. Life beyond pressure, darkness, heat, and movement. There is another quiet reason scientists approach certain parts of the ocean with caution. Life itself. In many of the ocean's most remote and extreme regions, biological systems operate under conditions vastly different from those near the surface. The growth is slow, energy is scarce. Recovery from disturbance can take decades or longer. In these environments, even careful scientific activity can leave lasting marks, which shapes decisions about where, how often, and how intensively research is conducted. Deep sea ecosystems are built on scarcity. Unlike surface waters, where sunlight drives abundant biological production, much of the deep ocean depends on limited energy sources. Food arrives slowly, drifting down from above, or emerging locally through chemical processes. As a result, many deep sea organisms grow slowly, reproduce infrequently, and live long lives. These traits allow them to survive in stable but resource-poor environments, but they also make them vulnerable. When disturbed, recovery is not quick. A damaged community may take generations to return to its previous state if it recovers at all. For scientists, this creates an ethical and practical dilemma. Studying life often requires interaction. Samples must be collected, cameras must be deployed, instruments must touch the sea floor. In regions where biological systems are robust, these actions may have minimal long-term impact. In fragile environments, however, the same actions can alter habitats permanently. Scientists are increasingly aware of this risk, and in some areas, they deliberately limit research activity to avoid causing harm. This restraint contributes to the perception that certain regions are avoided, when in reality, they are being protected. The distribution of life in the deep ocean is also highly uneven. Some areas support dense communities clustered around specific energy sources, while vast surrounding regions remain sparsely populated. This patchiness makes study difficult. A single expedition may encounter a thriving ecosystem in one location and almost nothing nearby. Interpreting these observations requires careful context, but gathering that context demands repeated visits and wide coverage, which are difficult to achieve in remote regions. Without sufficient data, scientists risk drawing conclusions that do not reflect broader patterns. Many deep-sea organisms are also highly specialized. They are adapted to narrow ranges of temperature, pressure, and chemistry. Small environmental changes can have outsized effects. Instruments that release heat, light, or noise may disrupt behavior. A sampling that removes even a few individuals can alter population structure. Over time, these impacts accumulate, especially in regions that are visited repeatedly. To minimize disturbance, scientists may choose to reduce activity or shift focus to less sensitive areas. Another challenge arises from the difficulty of observing biological processes without interference. In darkness, artificial light is required, but light can attract or repel organisms. Cameras may record behavior that is influenced by observation itself. Traps and sampling devices may capture organisms that would otherwise remain hidden. In environments where subtle interactions matter, these influences introduce uncertainty. Scientists must decide whether the data they collect reflects natural behavior or a response to intrusion. Long lifespans further complicate biological research. Many deep-sea species live for decades or even centuries. Changes in population size, age structure, or distribution may unfold slowly, beyond the timescale of most research projects. Detecting these changes requires long-term monitoring, which is difficult to maintain in remote and unstable regions. Without continuous observation, scientists may miss gradual trends or misinterpret short-term variation as meaningful change. The fragility of deep-sea ecosystems also affects equipment placement. Instruments anchored to the seafloor can damage habitats, crush organisms, or alter sediment structure. Over time, these physical impacts may change the environment being studied. Scientists designing experiments must consider not only data quality, but also environmental footprint. In regions where the risk of disturbance is high, they may opt for fewer deployments or rely on indirect observation, leaving gaps in data coverage. Biological uncertainty also intersects with other challenges. In regions with strong currents, organisms may be transported over long distances, blurring the connection between environment and population. In chemically active zones, biological responses may be rapid and localized. In tectonic or volcanic regions, habitats may appear and disappear as conditions change. These overlapping factors make it difficult to isolate cause and effect. Scientists may observe change without being able to attribute it confidently to a specific process. Because of these complexities, some biologically rich regions are studied cautiously rather than intensively. Scientists may prioritize baseline surveys, heat mapping, and minimal impact sampling. They may return infrequently, focusing on comparison rather than continuous observation. While this approach respects the environment, it also limits the amount of data collected. As a result, understanding of these regions remains partial. This balance between curiosity and responsibility is a defining feature of modern ocean science. Researchers are not only observers, but also stewards. They must consider the long-term consequences of their work, especially in environments that recover slowly. Avoidance, in this sense, is not withdrawal. It is a deliberate choice to protect systems that are vulnerable to disturbance. Weather above, chaos below. No matter how advanced deep-sea technology becomes, ocean science is still controlled by what happens at the surface. Wind, waves, storms, and changing sea conditions determine when ships can operate, when instruments can be deployed, and when research must stop entirely. For scientists studying the deeper parts of the ocean, this dependence on surface weather is one of the most frustrating and limiting realities. Even when conditions below are stable, the forces above can make access impossible, shaping which regions are studied and which are quietly avoided. At sea, weather is not a background detail. It is a governing force. Strong winds can generate large waves that make deck operations unsafe. Instruments that must be lowered carefully into the water cannot be handled when a ship is pitching and rolling. Cables can swing unpredictably. Heavy equipment becomes dangerous to move. In these conditions, even routine tasks are delayed. For regions where calm weather windows are rare or unpredictable, sustained research becomes difficult to schedule. Storm systems add another layer of complexity. Unlike land-based storms, which can often be avoided or waited out with minimal consequence, storms at sea affect every aspect of an expedition. High waves can persist long after winds subside, keeping seas rough for days. Visibility may be reduced by rain or spray. Navigation becomes more challenging. In extreme cases, ships must alter course or abandon planned work entirely. When storms are frequent in a particular region, scientists learn that even reaching the study site reliably is uncertain. Sea state matters as much as wind speed. Long period swells generated by distant storms can travel across entire ocean basins, affecting regions far from where the weather originated. A site that appears calm based on local forecasts may still experience large, rolling waves that make precise operations impossible. These swells are difficult to predict accurately and can persist even under clear skies. For deep sea work that requires stability, such conditions are enough to halt operations. Weather also controls timing. Many ocean research activities depend on narrow windows of opportunity. Instruments may need to be deployed at specific depths, during specific conditions, or in coordination with other measurements. A delay of a few hours can disrupt these plans. A delay of several days can cancel them entirely. In regions where weather frequently interrupts operations, scientists may struggle to collect complete data sets. Over time, this uncertainty discourages repeated attempts. And surface weather also influences safety. Research vessels operate far from immediate assistance. Severe weather increases the risk of accidents, equipment loss, and injury. While modern ships are designed to handle rough conditions, there are limits to what can be done safely. Scientists and crews must make conservative decisions, choosing caution over data collection. In regions where weather regularly pushes operations toward these limits, avoidance becomes a practical choice. Weather affects not only ships, but also the instruments they deploy. Rough seas can damage equipment during deployment or recovery. Sudden ship movement can strain cables, leading to premature failure. Instruments suspended in the water column may swing or collide with the ship or sea floor. These risks increase dramatically in unstable sea conditions. Losing expensive equipment to weather-related accidents is a real concern, and repeated losses can make certain regions economically unsustainable to study. Another challenge is unpredictability. Ocean weather can change rapidly, sometimes faster than forecasts can capture. A calm morning can turn into a rough afternoon. Winds can shift direction unexpectedly. Storms can stall or intensify. This uncertainty makes planning difficult. Scientists must build flexibility into schedules. But flexibility has limits. Ship time is expensive, and delays reduce the amount of work that can be completed. In regions where unpredictability is the norm, research efficiency suffers. Weather also interacts with other ocean processes. Strong winds can intensify surface currents, which in turn affect deeper layers. Storm-driven mixing can alter temperature and chemistry below the surface days later. For scientists attempting to isolate specific processes, these interactions introduce noise into the data. Measurements taken after a storm may reflect temporary disturbance rather than underlying conditions. In regions where storms are frequent, separating short-term variability from long-term trends becomes challenging. Seasonality plays a role as well. Some parts of the ocean experience predictable periods of calmer weather, followed by long stretches of instability. Research must be concentrated into these calmer windows. If weather patterns shift or shorten these periods, planned work may be postponed indefinitely. Regions with narrow operational seasons are particularly vulnerable to disruption, and repeated cancellations can lead scientists to redirect their efforts elsewhere. Weather also affects communication. Heavy seas can interfere with satellite signals. Rain and spray can reduce signal quality. In extreme cases, contact with instruments or support teams may be delayed. While these interruptions are usually temporary, they add another layer of uncertainty. In remote regions, even short communication gaps can complicate decision-making and increase risk. The cumulative effect of weather-related challenges is subtle but powerful. No single storm explains why a region remains lightly studied. Instead, it is the repeated experience of delays, cancellations, and losses that shapes scientific behavior. Over time, patterns emerge. Certain areas become known for difficult sea states, frequent storms, or unreliable weather windows. These reputations influence planning, funding decisions, and research priorities. Despite these challenges, scientists continue to push into difficult regions when the potential insights justify the risk. But they do so selectively, aware that success depends as much on the atmosphere above as on the ocean below. When weather consistently undermines the ability to work safely and efficiently, avoidance becomes a rational response rather than a failure of ambition. Communication limits and ocean isolation. In the modern world, constant communication is often taken for granted. Messages travel instantly. Data moves invisibly through the air. Help can be summoned with a signal or a call. But far from land, over deep and remote parts of the ocean, this sense of connection fades quickly. For scientists working at sea, communication is fragile, undelayed, and sometimes absent altogether. This isolation shapes how research is planned and explains why certain regions of the ocean are approached cautiously or avoided for long-term study. Water is an effective barrier to communication. Radio signals, which travel easily through air, are rapidly absorbed by seawater. This means that instruments deployed below the surface cannot transmit data directly to satellites or shore-based stations. Instead, communication must rely on cables, acoustic signals, or physical recovery of equipment. Each of these methods has limitations. Cables restrict placement and are vulnerable to damage. Acoustic signals travel slowly and carry limited information. Physical recovery depends on precise navigation and favorable conditions at the surface. In remote regions, these constraints become especially significant. Acoustic communication, often used to send commands to underwater instruments or retrieve basic status information, operates at speeds far slower than typical electronic communication. Messages can take seconds or minutes to travel, and data rates are low. This makes real-time monitoring impossible. Scientists may not know whether an instrument is functioning correctly until long after a problem has occurred. In regions where conditions change rapidly, this delay reduces the usefulness of the data collected. Isolation also affects problem solving. When an issue arises on land, it can often be addressed quickly with expert input or replacement equipment. At sea, especially far from shore, options are limited. A malfunctioning instrument cannot be repaired easily. Spare parts may not be available. Specialized expertise may be days or weeks away. Decisions must be made with incomplete information, often under pressure. In regions where failure is likely and recovery is difficult, this lack of immediate support weighs heavily on planning decisions. Distance from land further amplifies risk. Many of the ocean's most challenging regions lie far from ports and infrastructure. Reaching them requires long transit times, increasing fuel costs and reducing the time available for research. If an emergency occurs, assistance may be hours or days away. While research vessels are designed for self-sufficiency, there are limits to what they can handle. This reality encourages conservative choices about where and when to operate. Communication limitations also affect data quality. Instruments that store data internally must be recovered to access their full records. If recovery fails, the data is lost. In regions where recovery is uncertain due to weather, currents, or seafloor instability, the risk of losing months or years of information is real. Scientists must decide whether the potential insights gained justify this risk. Often, they choose environments where recovery is more reliable. Isolation influences coordination as well. Many ocean research projects rely on multiple instruments working together, sometimes spread over large areas. Synchronizing these systems requires precise timing and reliable communication. In remote regions, delays and signal loss complicate coordination. Instruments may fall out of sync. Data streams may become difficult to align. These challenges increase uncertainty and reduce the efficiency of research efforts. The psychological effects of isolation also play a role. Scientists and crew members working far from land experience prolonged separation from immediate support networks. Decision-making becomes more cautious when consequences are magnified by distance. Fatigue and stress can affect judgment. While experienced teams are trained to manage these conditions, isolation still shapes how risk is perceived and tolerated. Regions that consistently push teams toward their limits are often approached selectively rather than routinely. Isolation also intersects with safety protocols. Emergency response plans depend on communication and timely assistance. In areas where signals are weak or delayed, these plans become less effective. This does not mean operations cannot occur, but it does mean that acceptable risk thresholds are lower. Scientists may avoid deploying equipment or personnel in regions where communication gaps significantly increase danger. Over time, these factors create patterns of engagement and avoidance. Regions closer to land, with better connectivity and shorter response times, are studied more intensively. Regions far from shore, where communication is limited and isolation is profound, see fewer long-term installations and less frequent visits. This uneven distribution of effort is not a reflection of scientific interest, but of operational reality. Despite advances in satellite technology and autonomous systems, communication remains one of the ocean's most stubborn constraints. Improvements have expanded what is possible, but they have not eliminated isolation. The ocean still imposes distance, delay, and uncertainty, shaping where science can function reliably. Understanding the role of communication limits and isolation helps explain why some parts of the ocean remain lightly studied. It highlights how challenges that seem abstract on land become decisive at sea. When every decision must account for delayed information and limited support, restraint becomes a form of responsibility. Time windows and missed opportunities at sea. In ocean science, time is not an abstract concept measured only by clocks and calendars. It is a narrow window that opens briefly and closes without warning. Ships, crews, instruments, weather, and funding must align perfectly for research to succeed. When they do not, opportunities disappear. This fragile relationship with time is one of the least visible, yet most powerful reasons scientists avoid certain parts of the ocean, especially regions where conditions allow only rare and unpredictable access. Many ocean environments can only be studied during specific periods. Calm seas, stable weather, predictable currents, and suitable light conditions must coincide. These windows may last days, sometimes only hours. Outside of them, operations become unsafe or unreliable. For regions where these favorable conditions are rare, scientists may wait months or even years for an opportunity to return. If that opportunity is missed, the research plan must often be postponed indefinitely. Ship time is one of the most limited resources in ocean science. Research vessels are scheduled far in advance, often years ahead. Each expedition is tightly planned, with little room for delay. When weather or mechanical issues interrupt a mission, lost time cannot easily be recovered. A day lost to rough seas may mean an experiment is never conducted. In regions where delays are common, scientists face repeated setbacks that make sustained study difficult to justify. Time constraints also affect deployment and recovery of instruments. Many devices must be placed and retrieved during precise conditions. Currents must be manageable. Sea state must be calm. Positioning must be accurate. If conditions deteriorate at the wrong moment, equipment may have to be left behind or recovered prematurely. In some cases, recovery becomes impossible. Losing equipment is not only costly, but it also means losing the time invested in collecting data. The ocean rarely offers second chances. A failed deployment cannot simply be repeated the next day. Weather may worsen, schedules may not allow it, funding may not support another attempt. In remote regions, returning to the same location may require a completely new expedition, with all the planning and expense that entails. This reality weighs heavily on decision-making. Scientists must consider whether a region offers enough reliability to justify repeated attempts, or whether their efforts are better directed elsewhere. Seasonality further narrows time windows. Many parts of the ocean experience predictable seasonal changes that affect accessibility. Storm seasons, ice formation, monsoon cycles, and shifting currents all influence when research can occur. In some regions, these factors restrict operations to short periods each year. If those periods are disrupted, entire research programs may be delayed. Regions with narrow operational seasons are particularly vulnerable to missed opportunities and often see reduced scientific presence as a result. Biological timing also plays a role. Certain processes, such as migrations, blooms, or breeding events, occur within limited time frames. Studying these events requires precise timing. If an expedition arrives too early or too late, the opportunity is lost. In regions where access is uncertain, aligning research schedules with biological events becomes especially challenging. Over time, scientists may shift focus to regions where timing is more predictable. Time pressure affects decision-making at sea. When conditions are marginal, crews and scientists must decide whether to proceed or wait. Waiting may mean losing the opportunity entirely. Proceeding may increase risk. In regions where this dilemma occurs frequently, conservative choices often prevail. Safety and data quality take priority over ambition. This caution contributes to avoidance, not as a retreat, but as a calculated response to repeated experience. Long-term monitoring suffers particularly under time constraints. Sustained observation requires repeated visits to the same location, often at regular intervals. In regions where access is unpredictable, maintaining such schedules is difficult. Data gaps emerge. Instruments may not be serviced on time. Over years, these interruptions undermine the value of long-term records. Scientists may conclude that their resources are better spent in environments where continuity is more achievable. Time also influences funding decisions. Research programs are expected to deliver results within defined periods. Repeated delays and missed opportunities can jeopardize continued support. Regions that consistently disrupt schedules may be viewed as high-risk investments. This perception can limit future projects, further reducing scientific activity in those areas. The quiet pressure of time shapes ocean science in subtle ways. It does not announce itself like a storm or a current, yet it governs every expedition. Regions that demand patience, flexibility, and repeated attempts test the limits of what research programs can sustain. Over time, scientists learn where time works with them and where it works against them. Understanding the role of time helps explain why some parts of the ocean remain lightly studied when it reveals how missed opportunities accumulate, shaping long-term patterns of engagement and avoidance. When the ocean offers only brief moments to observe, and those moments are easily lost, restraint becomes a practical necessity. The cost of studying an uncooperative ocean. Every decision in ocean science is shaped by cost, even when that influence is not immediately visible. Ships, fuel, equipment, personnel, planning, and time all carry financial weight. While curiosity drives exploration, resources determine how far that curiosity can go. In parts of the ocean where conditions consistently disrupt research, cost becomes a decisive factor. Over time, economic reality explains why some regions are studied intensively, while others remain on the margins of scientific attention. Research vessels are among the most expensive tools in science. Operating a ship requires fuel, maintenance, crew salaries, insurance, and constant logistical support. Each day at sea represents a significant investment. When conditions are favorable and experiments proceed as planned, that investment yields data. When conditions are poor, time passes without progress and costs continue to accumulate. In regions where weather, currents, or access frequently interrupt work, the cost of failure rises quickly. Equipment adds another layer of expense. Deep sea instruments are specialized, carefully engineered, and costly to produce. Pressure-resistant housings, sensitive sensors, power systems, and communication hardware must all function reliably in harsh environments. When equipment is lost or damaged, replacing it is not simple. Lead times can be long. Budgets may not allow immediate replacement. In regions where equipment loss is more likely, scientists must weigh whether repeated investment is sustainable. Logistics amplify these costs. Remote ocean regions require long transit times, increasing fuel consumption and reducing time available for research. Supplies must be loaded in advance. Spare parts must be anticipated. Once a ship leaves port, resupply is rarely possible. Delays caused by weather or mechanical issues can extend missions unexpectedly, increasing expenses. In areas where such delays are common, costs can exceed projections, straining research budgets. Personnel costs are also significant. Ocean science relies on skilled crews, technicians, engineers, and researchers. Their expertise is essential, but it is not interchangeable or easily replaced. Extended missions, repeated delays, and challenging conditions can increase fatigue and turnover. Ensuring safety and well-being adds further expense. Regions that consistently push teams to their limits become harder to staff and maintain, influencing where institutions choose to operate. Funding structures shape behavior as well. Research grants are awarded with specific goals, timelines, and budgets. They are designed to produce results within defined periods. Regions that frequently disrupt schedules or produce incomplete datasets can jeopardize these goals. When projects struggle to deliver outcomes due to environmental challenges, future funding becomes uncertain. Over time, this creates a feedback loop. Areas that are costly and unpredictable receive less investment, leading to fewer studies and slower progress. Cost also affects technological development. Designing equipment to withstand extreme conditions requires significant investment in research and testing. While such advances expand what is possible, they also raise costs. Not every project can afford cutting-edge solutions. As a result, some regions remain beyond reach for routine study, accessible only to a small number of specialized missions. For most research programs, these regions remain impractical targets. The economics of risk play a role as well. In any research endeavor, some level of risk is acceptable. But in ocean science, risk is multiplied by isolation and cost. Losing an instrument in shallow water near shore is unfortunate but manageable. Losing equipment in deep, remote regions can represent a substantial financial setback. When the likelihood of loss is high, institutions may decide that the potential scientific gain does not justify the expense. Cost considerations also influence collaboration. Large-scale ocean projects often involve multiple institutions sharing resources. Coordinating such efforts requires alignment of schedules, priorities, and funding cycles. In regions where access is unpredictable, coordination becomes difficult. Delays affect multiple partners. Costs ripple outward. Over time, collaborative efforts may shift toward regions where outcomes are more reliable. It is important to recognize that cost does not diminish scientific value. Many of the ocean's most challenging regions are also among the most important for understanding climate, geology, and life. but science operates within constraints. Choices must be made. Resources must be allocated where they are most likely to produce sustained insight. In this context, avoidance reflects prioritization rather than indifference. Economic reality also evolves over time. Advances in technology may reduce costs or open new possibilities. Autonomous systems may lower the need for ship time. Improved modeling may reduce reliance on direct observation. As these changes occur, some regions may become more accessible. But until those advances are widespread and affordable, cost remains a limiting factor. Understanding the role of cost helps explain the uneven landscape of ocean science. It reveals how financial considerations intersect with environmental challenges to shape where research persists and where it fades. In regions where the ocean consistently resists study, cost becomes the final barrier, a reinforcing patterns established by weather, movement, depth, and isolation. As the documentary continues, attention will shift to how these constraints accumulate over time, leaving lasting gaps in data and understanding. The ocean's blank spaces are not the result of neglect, but of repeated encounters with limits that science must acknowledge.